Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at the energy contained within a system, which, because chemists are such clever namers, is called the internal energy. And one of the best ways to try and track the internal energy is by starting with the first law of thermodynamics. And this is originally stated as a law of conservation of energy. Energy can't be created or destroyed. It always has to come from somewhere, so it can only be moved around. So this is very similar to where we started this semester with the law of conservation of matter. However, this can often be rephrased as, again, the first law, which is a little bit more technical. It says the energy of an isolated system is constant. But if you think about this, comes to the same idea, because an isolated system has no energy coming in or out. No matter coming in or out. So anything in there has to stay in there. So any energy in has to stay there. So if energy isn't being created or destroyed, the energy of this isolated system has to stay constant. Now, we're going to try and keep track of this energy using the variable internal energy. So this is going to be the sum of all potential and all kinetic energy. And as such, what this lets us do is mathematically restate the first law as the change in energy for an isolated system equals 0. And we're going to go ahead and start from here. And this is one of the reasons why isolated systems mattered so very much, is because they let us track this change in energy. So the next neat trick that physicists propose is that saying, well, the entire universe, by its definition, includes all matter and all energy. So as a result, it's an isolated system. Nothing's coming or going. So that means its change in energy has to be 0. So we can then split up the entire universe into two things. What I care about, our system, which could be a beaker, and everything else. So the entire rest of the universe is called the surroundings. And by knowing that the entire universe is an isolated system, I know that if I add together my system and my surroundings, their change in energy, their net changing energy has to be 0, because energy can't be coming or going from anywhere. What this means is that if I know the change in energy of my system, I know the change in energy of my surroundings, as it simply has to be the negative of my system. So any energy my system gains has to come from the surroundings. Any energy my surroundings gain has to come from the system. So the next important thing to keep in mind is that when we're talking about internal energy, the exact value of the internal energy is kind of an arbitrary choice. We don't really know what it is, because it's going to be highly dependent upon, well, what types of potential energy I'm including. So am I including all the nuclear components, all the thermal components? I don't know. And as a result, instead of caring so much about the exact value of U, what we are going to focus way more on is the change in internal energy. I want to know how it increases or decreases when I expose it to a certain set of conditions or a certain chemical reaction. So we're going to be focusing almost exclusively on changes of energy, such as the change in internal energy. Now, this change in internal energy is known as a state function. This is a fancy way of saying that it only depends upon the initial and final conditions. So pretty much anything where I can put a delta in front of it is going to be a state function, because I can examine the change by just doing final minus initial. And as a result, this means that if I say start in state 1, I do all sorts of random things to it, going through states 2, 3, 4, 5, and I come back to my initial state, there was no overall change. We only care about where we started and where we end. Where we go in the middle doesn't matter. And this is going to be a feature of internal energy and other various metrics that we're going to mightily abuse when trying to come up with convenient ways to describe systems, because I might not know where I was in the middle, but as long as I know my initial and final conditions, I should be good. So we can then further look at this change in internal energy by limiting the ways that our energy can change. And we're going to focus on two major ways that energy can enter a system. One, through work. So either I can say put my my system can be a piston and I can do work on it. I can compress it, put energy onto the system, put it into the system, or by heat. I can heat my system up. It will gain energy that way. So when we're looking at this, we can just simply phrase the change in internal energy as the amount of heat added and the amount of work added. Now we're going to go ahead and pay a little bit of attention to the pesky issue of signs. So a positive change in internal energy means that I have built up energy in the system. The system has gained energy. And as a result, this means that a positive work means that work is being done on the system. So energy is entering the system through work. Now, one of the things I do want to make note, if you take a physics class, they will switch the sign convention on work. However, in chemistry, work will be positive. Similarly, if heat is entering the system is called endothermic, as it's taking in heat. So positive heat, positive work, positive internal energy change, all of these indicate energy entering the system. Conversely, if energy leaves the system, either net or individually in terms of work or heat, then it will have a negative sign. One of the special things I want to pay attention to is if we have negative heat. So if I have heat leaving the system, this is called exothermic. With heat, thermos, leaving, exo. So again, pay attention, positive heat, endothermic, negative heat, exothermic. So of all these three things, internal energy, work, and heat, the easiest one to examine is going to be work. So we're going to find a quantitative way to describe work, and then we can use that to help develop the relationship in between internal energy and heat. One of the we've already generated a brief description of the work of a system. So work can be modeled as simply putting a mass on top of a piston. So if I have a large mass, I'd expect the system to compress. So the piston would go down. I would have a negative change in height, but a positive mass and a positive gravitational constant, which means I need to have a negative sign out here to indicate that work energy is entering the system and I have a positive work. So again, gravitation is constant. Mass will be depending on how much mass is above the system, and I can measure that change in height. However, we know that we can relate this force of mass and gravity to pressure. We did a very similar problem when looking at gases. So let's go ahead and try and turn that mass to pressure. So we know that pressure is going to can be given as mass times the gravitational constant, so that force, over the area that force is applied to. Well, I can now combine these two equations, substitute in mass times gravity is going to be the same thing as pressure times area. Plug that in, and it turns out that work can be given as the negative of the pressure being applied to my piston times the area of the piston times the change in height. Well, here's a fun thing. That area times the change in height is going to be the change in volume of the piston. So as a result, this type of compression or expansion of a gas inside a piston is also known as PV work. So this is the work accomplished by a system expanding or contracting. While it is possible for PV work to be done by things other than a gas, as you might imagine, liquids and solids don't change volume quite so readily. So this is often explicitly directed towards gases, which works because we know how gases function fairly well. So what we can now do is combine this function of PV work with our previous description of internal energy. So I know that internal energy should be a state function, only depends on where I start and where I end. But part of the problem here is that heat and work are not going to be state functions. They're what we call path functions. If I put in a certain amount of heat, that does not guarantee that I'm going to have a certain change in internal energy because I know nothing about the work. So if I have a known amount of heat added to the system, change in internal energy is going to entirely depend upon the work. So, for example, if I have a negative work, this means I'll have a much greater change in internal energy. If I have a positive work, it means that I'll have a smaller change in internal energy. And as a result, anything where any sort of change that, first of all, does not have a delta, which heat and work do not, but also do not rely on where we started or where we end, are called path functions. So heat and work are the notorious set of path functions. However, I would really like to be able to study the heat and work of a system without having to worry about, well, the fact that they are path functions. So what we can do is, if I constrain what type of heat and work is done, then I can start to constrain heat and work to begin acting like path functions. So we're going to try and constrain heat to behave more like a state function, so I can learn more about the heat of a system. And one of the simplest ways of doing this is by replacing our work with our PV work. This means that I can now relate the change in internal energy, the change in heat to the change in internal energy, as long as I know the pressure and the change in volume of a system. So one of the easiest ways we can do this is if I don't allow the volume to change. So if instead of putting the system in a piston, I put it in a box, volume can't change, so there's no PV work at all. And under these conditions, so we call these constant volume conditions, then heat will be the same as internal energy. And this means that heat starts acting like a state function. I can figure out the amount of heat entering or leaving a system as long as I know the final and initial conditions as guaranteed by internal energy. So this set of constant volume conditions is also known as isochoric. Iso, constant, choric, volume. So if I ever use isochoric, this is me just fancily saying constant volume. And if I measure my change in internal energy under isochoric conditions, I can determine the exact amount of heat entering or leaving the system, which will help me predict, well, a lot of things about how much energy is in the system, as well as how much I may be raising the temperature outside. However, one of the important things to make note of is most systems aren't going to be under constant volumes. If I'm doing a chemical reaction, I'm usually not doing it in a closed box. So next time, we're going to be paying a lot more attention to constant pressure. This is also known as isobaric conditions. And instead of using internal energy, we're going to introduce the idea of enthalpy. Until then, take care.